So we've talked about mass spectra before, and so we want to go into how a mass spectrometer works. So here are some things that you need to know. This is an IB specific topic, how a mass spec works. And then we'll go through and do some sample calculations as well. So it says the mass of individual atoms may be determined using this method. We can also use this method to determine the average atomic mass for an element. So this is going to give us some information regarding the quantity or percent abundance of each isotope for an element. So here's how it works. The principle behind this is that a positively charged particle that passes through a magnetic field is deflected along a circular path that is proportional to the mass to charge ratio, or M/Q ratio. So here are the steps. These are important as well. You know the steps that take place. Start off with a substance and you need to vaporize it. So you need to turn it into a gas. And then the next step is to ionize this gas. So vaporize first and then ionize. It says the vapor is ionized by bombardment of high energy electrons that produce positive ions. So essentially you knock an electron off of the atom, producing a positive ion. The ions produced then pass through holes in parallel plates where they are accelerated. So you have a magnetic field that accelerates the positive particle. Not only that, the ions are deflected by this magnetic field. Here's the important part. It says the amount of deflection depends on the mass and charge of the ion. In practice, though, only +1 ions are produced. So you take all your substances, you knock off one electron. So all of the ions have a +1 charge. And so really the amount of deflection depends solely on the mass of the particle. So let's take a look at an example using carbon dioxide. So carbon has 3 isotopes, carbon-12, carbon-13, and carbon-14. And so in carbon dioxide then, we're going to have carbon dioxide molecules that differ in mass by 1 each. So we have 44, 45, and 46 AMUs for these molecules. And so if we look at what happens, so we have the substance enter the magnetic field. The heavier particles are less easy to cause their path to bend. They tend to travel in a little bit more of a straight path. And so what's going to happen is the distance traveled by the lighter mass particles will be smaller or shorter. And so those lighter mass particles are going to come to the detector sooner or quicker. So you'll be able to detect their masses sooner. You'll be able to then determine the relative number of particles that have each of those masses, and then you produce a graph like we've seen, a mass spectrum, where you have different peaks for different masses of a particular substance. So again, the key is that we have less deflection in a larger mass particle or more deflection in a smaller mass particle, causing those particles to reach the detector at different times. And then again, we can determine the relative abundance of each of those particles and end up with a graph like what's shown on the next page. So here's a sample mass spectrum for germanium. So on the y-axis, we have the detector currents. So this will allow us to determine the relative abundance. I've mentioned before that sometimes these peaks add up to 100 if these are percentages. They don't always have to add up to 100. In this case, they do not. So we want to look at the relative abundance based on each of the peaks, and then as we'll see, the total of each of those peaks. X-axis, our mass to charge ratio. So really this is just mass, again, because all the particles have a +1 charge. And so 70, 72, 74, 76 AMU, these are the masses of the different atoms of germanium. So let's take a look at some calculations. Pause the video if you need to finish filling this out. So our first step is to determine the total detector current. So go ahead and take each of those peaks, add them up, and see what you get. Go ahead and pause the video while you do that. So the sum of all our individual detector currents give us 33.33. Our next step is to determine the relative abundance of each isotope. We can convert that to a percent abundance as well. So let's do that. So for germanium 70, if we go back to the graph, the relative or the detector current for germanium 70 is 6.83. I'm going to take that and divide it by the total detector current. And then we'll convert this to a percentage by multiplying by 100. Go ahead and pause the video, see what you get. So what this means is that about 20.5% of the particles that pass to the detector, reach the detector, have a mass of 70 AMU. Now let's go ahead and do the same thing for another isotope, germanium 72. Again, going back to the mass spec, the detector current for that particular isotope is 9.13. Again, divide by the total detector currents, multiply by 100. Go ahead and pause the video and get that number. So again, what this tells us is that 27.4% of all of the particles that reach the detector have a mass of about 72 AMU. We can continue with this process for each of the isotopes. Knowing the percent or relative abundance of each isotope and the mass of each isotope, we can then determine the average atomic mass like we have done before. So that's what a mass spec looks like. That's how it works. And again, just make sure you know the steps. Make sure you know overall what's happening in that device. All right, thanks for watching.